Swayam Prabha. Digital India. Educated India.
Now, we have already seen the theory of how to handle less than equal to constraints, and also we covered some examples on less than equal to constraint, and towards end of the previous discussion we also looked into how we would handle these equality constraints in theory when we talk about simplex method. Now going forward, we should see one example to get full hold of this concept of handling equality constraint. So again, it's a very simple problem that I have stated in two variables here, 5 variables but with 2 constraints. Here problem is that we have to minimize a function 2x1 plus 3x2 plus 2x3 minus x4 plus x5, and it is subject to 2 constraints and both of them are equality constraint. Now you clearly see a problem that if I start making the simplex tableau with these equality constraints, the problem is that we would not be able to see the form where we want one coefficient to be exactly 1 for initially chosen basic variable and so on. So that is why we would introduce something called as artificial variable. Now problem with artificial variable is that they would not help us in any capacity in these constraints 1 and constraint 2, because in a real system they do not exist. For example, if I add certain term S1 here and certain term S2 here, what we were doing when we were dealing with less than equal to constraints, we were able to write that S1 should be greater than equal to 0 and S2 should be greater than equal to 0. However, when I am dealing with equality constraints, the problem is that since I have artificially introduced S1 and S2 because they are not part of the original solution, S1 should be equal to 0 and S2 should be equal to 0. By doing this, I will have the canonical form. I can easily put x1, x2, x3, x4, x5 equal to 0 and get my first solution of S1 equal to 0 and S2 equal to 2. Now S1 equal to 0 is fine, but S2 equal to 2 is not possible, because the moment S2 becomes 2, this constraint 2 gets violated. And the reason is that it is not present in the original solution. So any solution for which any of the variables x1 to x5, if it takes any non-zero value, my constraint 2 is guaranteed to be violated. As a result of which, equality constraints add another layer of problem, that we introduce something called as artificial variables that we have to eliminate as we progress towards the solution. Going forward, our mathematical understanding and application would be exactly same what we learned in less than equal to constraint handling, that how to decide the entering variable, how to decide the leaving variable, but we have to do one mathematical trick here. And that mathematical trick is that we will introduce these two artificial variables y1 and y2 and induce another equation we call as infeasibility form. Infeasibility form is that y1 plus y2 is equal to w, if I write it simply. Now in this case, since these are artificial variables, by the end of my simplex W, we should ensure that W takes the value of 0, because we would be writing general condition that y1 should be greater than equal to 0, y2 is greater than equal to 0. We already learned that having any non-zero values of y1 and y2 would violate our consistency of given constraints. So, for W to be 0 and y1 and y2 to be greater than equal to 0, and infeasibility form of the form that W is equal to y1 plus y2, the only solution that would be admissible is that when y1 and y2 both becomes equal to 0. That is why I termed this entire step as a mathematical trick, that although I am inducing a new equation, this new equation is not altering the behavior of original system, because by the end of calculations I will be able to eliminate these artificial variables. Now please note that I am not calling artificial variables as slack variables, because slack itself tells us that if constraints represent the resources, how much additional resources we would have after we have reached the optimal solution. So that is the word slack would represent. On the other hand, artificial variables are artificially added to the system and they do not carry any physical significance or relevance to the solution, and hence should be eliminated from the system as we converge towards a feasible solution or optimal feasible solution. So when we introduce these y1s and y2s into our system, this is how our two constraints are going to look like: the original equation plus artificial variable, the original equation plus artificial variable, and B remains same, that is 0 and 2. Now what we do is that we add these two constraints 1 plus 2 and we subtract it from the infeasibility form, as a result of which we get another equation minus W minus 4x1 plus 2x2 minus 5x3, x5 will get eliminated, and y1 plus y2 both are captured in this infeasibility form. So W would carry the information about this y1 and y2. Now as we do all these steps, you see that we are consistent in our mathematics. What I mean by consistent in mathematics, that we have not violated any linear algebra operation. I am just writing an equation. I am ensuring that once I reach a solution, these artificial variables are eliminated. I am just adding these two equations systematically, subtracting it from third equation. While it of course looks like an additional mathematical step, but this is taking us towards elimination of artificial variables systematically. Now what I do here is that I write my simplex W in exactly similar fashion as I did for less than equal to constraints. That is, I will write y1 and y2, my first two basic variables, and every other variable becomes non-basic, which I force to take value equal to 0, and the coefficients of last equation that I got gets written with minus W plus 4x1 2 5 minus 5 0 2, all of them are written in same sequence. So this is the same simplex W. Now here I clearly see that y1 is equal to 0 and y2 is equal to 2. So of course this is not acceptable to me because artificial variable should be equal to 0. So what I have to do? I have to apply the same trick, that I will introduce one variable, ask another to leave, and if there is indeed a feasible form of this equality equation, I should be able to eliminate both of these artificial variables. So let us see that how it looks. I will first of all enter the variable which has most negative coefficient. In this case it's minus 5. I will do all the steps again that is look into that which particular ratio is minimal, ask that ratio to leave and perform the operations as we have learnt here, that this 1 should be equal to 1 minus 3 into 3 divided by 2 and so on. I will of course not repeat the calculations here, we have already learned this in updation of simplex W here, but I will apply the same operation as I was doing earlier in case of inequality constraints or less than equal to constraints, and keep on updating the W, and I will keep on doing as systematically I was doing before. Please note that my objective function is also represented here. As these variables are entering and others are leaving, all the coefficients will get updated as per the rules or algorithm that we have identified of applying the operations in our earlier calculations. So, we get our first updated W here and so on. So, now what we will do, our next variable will enter which has maximum negative coefficient as a result of which we will eliminate y2 in our next calculation, because here ratio becomes not applicable. Why? Because this coefficient is already less than 0, as a result of which this would not be a binding constraint. So, we would have no choice but to eliminate y2 from the solution. As we do this, you would see that in couple of iterations we will end up with the form which looks something like this. Now, in this updated form, you would see that all the coefficients in the last row happens to be 0. Now, this entire row becomes not important for us in subsequent W's, and you also see that y1 and y2 are also out of the solution. That means y1 and y2 now actually becomes equal to 0, and this is exactly what we wanted when we set up these artificial variables. That means this W would have one feasible solution going forward, and we should be able to solve this particular equation. Now, there is also another takeaway here, that here since we are talking about two constraints to be strictly met at a particular point, many times it will happen that equality constraint problem would hit the problem of infeasibility very frequently, because there is no slack, as the name suggests here. There are no resources that we have available that has to be in the situation of less than equal to or greater than equal to, as a result of which chances of finding the non-feasible solution in equality constraints are much higher when these problems would be applied to infrastructure systems, planning, decision making and so on. Now, once we have eliminated our artificial variables from the basic feasible solution, the further progressions happen in exactly same manner as we have done earlier. That is, we will again identify a particular variable with most negative coefficient, bring it into the solution, would eliminate the other variable based on the calculation that we do in the tableau. Of course, I would not worry about the exact calculations here, because we have already done a very detailed example in our earlier discussions. But here after couple of iterations, as if we are solving an inequality or less than equal to constraint problem, we would end up with our final solution which would give us that value of f, in this case come out to be 2 by 5. And at optimality you get the value of x4 as 2 by 5, x5 as 4 by 5, and all other variables come out to be 0, and this happens to be our optimal solution for the equality constraints. So, to sum it up, whenever we are dealing with equality constraints, rather than introducing a slack variable, we introduce an artificial variable to get our solution into canonical form, and then our first attempt is to eliminate those artificial variables from the solution, and we keep on progressing sequentially as if we are solving inequality constraints or less than equal to constraints once our artificial variables are eliminated. Typically, we also write, in addition to objective function, an additional row which adds the feasibility or subtract the feasibility from the feasibility equation from the sum total of the constraints. That is done to ensure that that y1s and y2s are not there in our last column, otherwise they would again keep on re-entering and may increase the iteration time. So, the fundamental does not change. Now, on similar lines, we can also talk about handling greater than equal to constraints. So, one way to handle greater than equal to constraint, so if I have a constraint of form Ax greater than equal to b, I will multiply both sides with minus and I can have this constraints as Ax less than equal to b and then again I have negatives on both sides. Be careful here that I cannot just simply cancel the negatives on both sides because I am dealing with greater than equal to or less than equal to constraints. I have to make sure that whenever the equation is multiplied by negative sign, the greater than equal to flips the sign and becomes less than equal to and vice versa. Now, the problem here is that when we discuss the fundamentals of simplex method, we said that b is greater than equal to 0. If in our original system, if b anyways is greater than equal to 0, the moment you multiply it by minus 1, the RHS in this case minus b becomes less than equal to 0, as a result of which rules of simplex would not apply. So, in many cases this particular multiplication is not going to help us with the simplex tableau or simplex calculation. So, what we do is that we again have to involve an additional step to convert these greater than equal to constraints to less than equal to constraints without violating the form that b is greater than equal to 0. So, as we learnt that simplex method is tailored for less than equal to constraints, we have to ensure that b is greater than equal to 0, and all these things are necessary for establishing an initial feasible conditions, that is when we will introduce a slack variable or artificial variable. We are doing that so that our first solution is basic feasible solution, and then what happens is that to do that we may have to introduce some additional variables like artificial variables, as we did in the case of equality constraints. Same treatment would be done for greater than equal to constraints. So, what we do here is that if I have a simple example that z equal to 2x1 plus 3x2 and it is subject to x1 plus x2 greater than equal to 5 and x1 x2 greater than equal to 0, what I will do? I will add a surplus variable. So, earlier we were introducing a slack variable in less than equal to constraint, but to make it an equality constraint, I cannot add a positive number because in this case left hand side is already greater than right hand side. So, if I add something to already greater value, it is certainly going to increase in a magnitude, because I am also bounded by another constraint that all the variables that I am dealing with in my system should be greater than equal to 0 for simplex method to work. Hence, I will introduce this variable, what I am going to call as surplus variable, with a negative sign. Now, the problem that happens here is that with this introduction of negative sign, I still do not get canonical form, because canonical form wants coefficient to be plus 1 only one time for the basic variable, as a result of which I cannot call this equation, or even for that matter if I have multiple equation. So, just like x1 plus x2 greater than equal to 5, let us say I have another equation 2x1 plus 3x2 greater than equal to 7. I am just hypothetically writing these equations. So, if I convert them to equality sign, I will introduce one slack variable here, I will introduce another slack variable here, something like this. You would see that although the absolute magnitude of coefficient is 1, with the sign they become minus 1. So, canonical form is not ready. Now, whenever I do not see a canonical form immediately after introducing these variables, I will again restore to adding the artificial variable, as I did in case of equality constraint. So, this is exactly what I did when I was dealing with equality constraint. And the moment I introduce this artificial variable, I end up including another variable w is equal to a1, which is in line w is equal to y1 plus y2 when we were dealing with the example of this artificial variable. So, our first objective now again would be similar to what we did earlier, that is we will drive a1 to 0 and find a feasible solution to the original constraints. Once it is out of the picture, we will keep on updating our tableau as we were doing earlier until we reach our optimal solution, that is there is no other variable to enter, there is no other variable to leave, and with this we should be able to arrive at our optimal conditions. Now that we have learned this very elegant yet powerful method called as simplex method, let us try to find some use cases in our infrastructure systems problem. We will of course further elaborate in subsequent discussions on the similar examples, but I think it is important to see that where all the mathematics tricks that we have learned would be applied. So, as water resource managers, one typical problem that water resource system operators and managers face is to minimize cost of sourcing water from multiple reservoirs. So, for example, there is one reservoir located in state A and there is another reservoir located in state B, and state C happens to be downstream of both these reservoirs. So, they will withdraw some water from state A, some water from reservoir in state B. State A may charge them x1, state B may charge them x2. Individual states would also have constraints on the availability of water and so on. But for state C or a region C, the objective would be to minimize cost of sourcing water while ensuring that their demands are met. So, there are constraints of course that sum total of water from each reservoir should be greater than city demand. Each reservoir also has a maximum supply limit, and water flow meets certain quality or mixing constraints, that is it is also mandatory that x1 should be greater than certain amount or x2 should be greater than certain amount or less than certain amount, depending upon that if x1 water is not as high quality water as x2, you would want that the resultant concentrations to be still within the tolerable limits. As a result of which both economical, engineering and public health constraints come together to give a rise to an optimal problem, and in this case our decision variables simply become water quantity drawn from each reservoir. Now, although this particular problem involves multiple stakeholders, multiple partners, we can always make it a very non-linear problem in terms of costing, etc. But the first starting point even in real world is always to express these objective functions and constraints in as linear way as possible, because we are not just interested in an optimal answer, we are also interested in the sensitivity analysis. That is, what would be the additional cost that we have to incur if we want to withdraw one extra unit of water from reservoir B while ensuring that the system is operating as per plan, and that is where linear programming problems become very, very important. For transportation engineers, linear programming problem has been widely used in classical transportation problems. One such example of transportation problem is to maximize the network efficiency. When we talk about network efficiency, we essentially mean that we are minimizing the travel time while traversing over the entire network. So, for example, if somebody has to go from location A to B and multiple routes are available, some of them are direct routes, some of them are via routes, depending upon condition of these roads or width of these roads will have certain carrying capacities, and also some of them may be passing through very busy areas like schools, hospitals, etc. So, you may have to also limit number of traffics that can flow on these roads in the peak time, and one way to do that is that we impose speed limits into these particular regions. So, while our objective is to maximize network efficiency, we cannot have highways or freeways built in the entire city. So, constraints come into picture. One such constraint is that the traffic flow should be greater than equal to certain value or should be less than equal to certain value, depending upon we are talking about a highway road or a intra-city road. Second is that we would always have the budget constraints. Ideally, we would want every road in the city to look like a highway, but we understand that from logistics perspective, from economics perspective, that is certainly not feasible. Not only there are land constraints, there are also financial constraints. Even on a government land, building or making a 6-lane highway is going to be way more expensive than making a 2-lane highway or a 3-lane highway. So, there are cost limitations that are involved. Also, there would be demand constraints for passengers or freight between a particular nodes. That is, between two pair of nodes, you would always want to make sure that the traffic is always less than this or greater than certain amount, so that it caters to large population and so on. So, it again can be represented as a problem of optimization, where our decision variables become that how wide should be each road, what should be length of each road, and what should be the value of flow on each link in the network, so that the efficiency is the highest. Now, again, such a complex problem can always be linearized to get first order insights into the operational characteristic of such system. And finally, let us look into one more example which relates to an infrastructure in the power domain. That is, our objective would be to minimize generation cost, and in today's world, in 21st century, we also talk about emissions, that it's not just energy generation that you have to maximize, you have to also ensure that your emissions are minimized. Now, when we talk about emissions, if we are talking about a thermal power plant, these thermal power plant may use coals of different type. It could be anthracite, it could be bitumen, or it could be lignite. Now, if we talk about Indian mines, most of the Indian mines would produce coal which is of relatively high ash content or typically in the lignite category. So, what these thermal plant managers may have to do is that they may have to find the sources of anthracite which are not necessarily located somewhere in India, as a result of which, while their emissions will go down, the cost of acquisition of the same amount of energy will also go up, because transportation cost becomes a significant portion of the overall costs of operation. And that is where optimization comes into picture, that while maintaining certain level of energy generation, how I minimize emissions, these emissions which in turn are tied to the technology of production and raw material of production, and there may be production constraints of the raw material itself. Also, on infrastructure side, we may have the generation capacity limits, that if you have installed generation of certain capacity, it should always be above certain load factor, or certain generators should never exceed certain load factors. Transmission lines would also have the flow constraints for that of what capacity I should be providing a particular transmission line. There should be demand at the consumption point, because if these transmission lines are provided, the cost recovery also comes into picture. So, combining this entire narrative, that what guides the power supply and demand, this again becomes a problem which has an objective function, constraint, and of course decision variables, which becomes that how much power should flow between a particular pair of nodes, what would be the power generation from each plant, how much coal would be acquired from Australia or Indonesia versus how much coal would be purchased from our own mineries, and so on. And again, the one of the good starting point is to linearize this system and solve it using the tools that we have already learned. So, the conclusion of our discussion on simplex method is that simplex method is indeed a very elegant and robust method when we have linear system of equations, that is linear objective function, linear constraints, and we find ways to put it into simplex framework simplex method will always guarantee global optimality as it traverses from one extreme point of a convex feasible region, and whenever we are dealing with convex feasible regions, our local maxima or minima is guaranteed to be global maxima or minima. We also learned that when we are dealing with equal to constraints or greater than equal to constraints, we need to have possibility of surplus and artificial variables so that we can follow the mathematics that we have learnt in simplex calculations. We also learnt about some tie breaking rules, that sometimes there is also a risk that same variable is leaving, same variable is entering, as a result of which number of calculations or iteration steps become higher. So, a very simple bland rule was proposed to break this tie that we already discussed. We also learned that expressing a system of equations or a real world problem into system of equations does not guarantee that a solution would be of our liking. There may be some degeneracy, particular set of equations may be infeasible, that is, you cannot have two constraints of type that 3x1 plus x2 is greater than equal to 4 and 3x1 plus x2 is also less than equal to 4 when x1 is greater than equal to 0. This seemingly simple example here may appear very stupid in some sense, in a sense that how we can say that, but when we are dealing with real world problems, sometimes we tend up writing our constraints which are not compatible with each other. So, these particular constraints should be identified beforehand, that which two constraints would not go together in a particular system of equation or are incompatible with each other, and that may not always be that easy to identify in real world systems, but once that happens, you would end up with infeasible solutions or solutions that have no value or are trivial in nature. Going forward, we will learn about something called as duality theory and sensitivity analysis as applied to simplex method, and also those who want to use these techniques at a research scale or commercial scale, they do not necessarily have to do iterations by hand always. There are multiple packages, programs, softwares that are now available, are industry ready, and in fact are being used by diverse sets of industry such as Pulp, Pyomo, SciPy.optimize. All of them have capability to solve linear programming using simplex method or Lagrange multipliers that we have discussed earlier. Similarly, MATLAB, R are also equipped with packages and libraries that are capable to do so. At commercial scale, there are certain platforms like Cplex, Gurobi, Mosaic that have been used, but what is most important to know that the underlying principles of all these softwares, libraries, packages remain the same, that how we reach to our solutions once we are dealing with large number of constraints, equality, inequality, constraints, less than equal to constraints. So, the fundamental remains the same, but most importantly from the perspective of infrastructure manager, operator, designer, it is important to formulate the program as a linear programming problem, because if you do not have a problem, all these packages become just another line of code, because you do not know or you do not have an exact utility of these programs if there is no problem. And then of course, you have to express these into standard form before we feed into these particular softwares. We can use these built-in solvers, write our own simplex code, and finally, once we have some optimal value, we have to translate our discussions into interpretations for real world and look into the practical feasibility beyond mathematical feasibility. So, that is all from the concept of simplex method. In our subsequent discussions, we will look into the concepts of duality that bridges the gap between the engineering perspective of optimization and economist perspective of optimization. Thank you.